LeBron James.
Scream if you love recurrent neural network.
神说，诸水之间要有空气，将水分为上下。
But no matter how much LeBron loves RNN, it still couldn't win against the Transformers. Because attention is just way too powerful. While we did have contestants like RWKV, Mamba, and XLCM joining the fight, and even have these RNN-inspired methods perform decently on benchmarks, they still were not able to practically match up to the bar that the Transformer-based models have set, especially the larger you scale them. Mamba certainly was the only strong cope, but seeing not much significant progress being made in the field along with the lack of expertise in making Mamba-based models, other companies have focused on further developing Transformer-based models instead. While we do see some other Mamba developments like Jumba, Mamba 2, and Mamba Vision, it was still kind of neglected, similar to your personal data on the internet. In today's age, data brokers have become a significant privacy concern. These companies collect, aggregate, and sell vast amounts of personal information, and we're potentially talking about your name, logins, addresses, your online activity, and even your social security number. This extensive data collection doesn't just lead to annoying spam calls, it also puts you at risk of identity theft. To add to that, there's also another major issue, which is people search sites. These platforms create detailed personal profiles of millions of Americans, pushing them online for people to access. Imagine having your personal details just a few clicks away from potential scammers or stalkers. It's a pretty terrible situation, shout out to the US legislation, and this is where Incogni comes in. Incogni reaches out to data brokers on your behalf, requests your personal data removal, and deals with any objections from their side. While they do have your information, they are still legally obligated to take it down when requested. With the family and friends plan, you can also add up to 4 members to your subscription, meaning that they will benefit from the same exact service you get. And since many data brokers will continue to collect your personal information even after they have removed it, they also take care that your data stays off the market by conducting repeated removal requests. This means that whenever a new record pops up on a data broker side, Incogni will automatically take care of it. While you can certainly do this yourself, you would still have to keep track of it every month, which is not ideal. That's what makes your yearly subscription especially advantageous, and Incogni will continue to protect your data privacy for as long as you use the service. Keep in mind that the service they provide ranges from the country you reside in. They currently also have a 60% off and a 30-day money-back guarantee, which gives you no risk in trying out. So check out Incogni now using my code BYCLOUD with the link down in the description, and thank you Incogni for sponsoring this video. Anyways, why does Mamba fall short in the first place? Mamba 2 actually came out recently, and it addressed some of the problems that Mamba 1 has, like proposing state-space duality to address the small state sizes, which limited Mamba's performance, and structured mask attention to create a Mamba attention hybrid model that maintains good memory recall cheaper than your typical attention. And that is definitely a great solution, but most of you probably became dizzy after hearing those improvements. On one hand, Mamba 2 is still a bit too new to really know if it's actually good or not, and on the other, it might not be satisfactory for some people, as something fundamentally and architecturally different might be worth exploring too. So we are back to the drawing board. Okay, so Transformer is good but suffers from quadratic complexity. RNN-inspired methods like Mamba do offer a linear complexity alternative, yet when it is supposed to shine in long context, it still struggles to take advantage of the extra information it is being conditioned on. Like logically, tokens later in the sequence should be easier to predict on average, since they can be conditioned on more information, right? And Transformer does well on this, while Mamba falls short. This is because unlike Transformer's self-attention that is simply converting the context into an information lookup table, Mamba has to compress everything into a fixed size of hidden states, then at some point, information or content would just leak out and be forgotten. So basically, a better compression heuristic is needed for RNN-inspired methods. To clarify a bit, the compression heuristic is the idea that the ability to compress data is closely related to understanding or learning the data. In other words, if you can represent information more concisely, you likely would have a good model or understanding of the underlying patterns. So what other mechanisms would have the ability to discover the underlying structures and relationships among thousands or potentially millions of tokens? Well, machine learning, that is. More specifically, self-supervised learning learning. It can compress a massive amount of data into the weights of a model and would usually demonstrate a strong understanding about the semantic connections within the data. Wait a minute, what exactly are they cooking? To retain the linear complexity, they chose to build upon RNN, and instead of doing anything wonky, they straight up chose violence. Hidden states? We don't need them, let's just toss them off the bridge and replace them with come here. It's machine learning models. Oh my god, alright, I'm done. Back in the good old days, we had stack more layers, and now we have, let's see how many ML models we can shove into an RNN. It's like when you put a microscope on the RNN, you would just see a tiny little ML models running it. But with all these, it is now able to replicate the effect of self-supervised learning within the hidden state. Well, technically the hidden state has been now replaced by the ML models, but this does theoretically unlock the ability of linear complexity architectures having an expressive memory, which then allows them to be trained on millions or hopefully billions of tokens and perform some crazy in-context learning. However, with this huge structural change, how it works now is fundamentally different from what we are used to. So in this paper, Learning to Learn at Test Time, RNNs with Expressive Hidden State, proposed the idea of TTT, Test Time Training, which is a new class of sequence modeling layers where the hidden state is an ML model, with its update rule being a step of self-supervised learning. They named it TTT because of the fact that updating hidden states in this model basically resembles training tiny ML models during inference, hence test time training. That does kind of sound like cheating, where it is literally training on the test data, but it is a bit different as it is using the ML models to compress the context, similar to how self-attention uses a KQV to create a compressed representation of the relevant information. Both methods are not memorizing specific answers, but rather learning to efficiently encode and retrieve relevant information from the context. To comprehend the idea easier, self-attention can be interpreted as having a hidden state growing with context, therefore has a growing cost per token, which makes its complexity quadratic. But for the naive RNN and TTT layer, both are compressing the growing context into a hidden state of fixed size, therefore their cost per token stays constant, so that's why they have a linear complexity. However, TTT's compression is being updated or trained every step, which allows the model to adapt to the current input dynamically. So TTT is basically a component replacing the attention mechanism by using an ML model to compress the context into a fixed size without a growing need in computations, which is having that quadratic complexity. Now, you can probably imagine that there are two different loops going on within TTT. One is what they call the inner loop, that is the process of training the hidden states ML model on the context. So when you feed it a prompt, the inner ML model is literally doing gradient steps on the tokens, which is pretty much doing explicit active learning where the context is being burned into the parameters of the network. Then the other is the outer loop, which is training the overall big model that encompasses the overall sequence processing. And for an ML model to achieve self-supervised learning, a task would need to be defined. So this is where the outer loop comes in. For self-supervised learning tasks, the goal is usually set by humans, right? But since humans are not cool anymore and AI is cooler, let's just make the goal for the outer loop about learning how to set the self-supervised learning tasks, so humans can be removed from the process. So by sprinkling some more parameters in the outer loop, this can then be converted into a learning to learn paradigm, which adds more learning flexibility to the self-supervised task for the inner loop. This meta-learning is probably the best way to compress context flexibly, which would help the process of next token prediction. And if you look closely at the title of this paper, you would find that the parenthesis is actually referring to the inner loop and the outer loop. A pretty sick Easter egg, right? So the ML models that you pick for the inner loop does matter a lot. In the paper, they have implemented the ML model with either a linear model or a two-layer MLP model. They didn't choose these ML models randomly either. In the paper, they theoretically proved that the TTT layer with a linear model is equivalent to linear attention, which is simply self-attention without the softmax. This is able to happen because in the outer layer, they added the QKV projection matrices, which are learned during pre-training. And this addition has made TTT mathematically the same as linear attention. So when the authors mentioned that TTT replaces attention, it is literally doing that. What's even better is that TTT layers have the same interface as RNN layers and self-attention, therefore can be replaced in any large network architecture like a plug-and-play type of layer. So to find out what works the best with TTT layers, they have tested it on the backbone architecture of Mamba and Transformer, denoted as M or T. And the combo of different backbones and different ML models within the TTT layers have some pretty interesting effects. context. Overall, TTT layers with Mamba backbone perform better in general, and within the Mamba backbone, TTT MLP at best is only comparable to TTT linear, but with the transformer backbone, TTT MLP is better than TTT linear. The authors theorized that the temporal convolutions in the Mamba backbone helps more when the sequence modeling layer has a less expressive hidden state. So as the linear model is typically less expressive than the MLP model, TTT linear then benefits more from the convolutions that the Mamba backbone has. Training a network with TTT layers also works the same way as training any other language model such as transformers. The same data, recipe, and objectives such as next token prediction can be used to optimize the parameters for the rest of the network. Now, here comes the most juicy part. Does TTT really outperform transformers? The short answer is yes, but the long answer is only if you compare it fairly. In their largest experiment that is trained on the Pile subset called Books 3, with 5 different models at 1.3 billion parameters all trained from scratch, both TTT Linear M and TTT MLP M perform better than Mamba beyond 8K context length and up to 32K context length. Even TTT MLP T performs slightly better than Mamba at 32K context too. While transformers do win in terms of perplexity, if you do look at them matching their training flops at 32K context, 3 out of the 4 TTT outperforms Mamba and Transformer. This shows that TTT is also superior in terms of compute versus performance. It is also interesting to point out that within 2K context, Mamba was the overall winner. But how come in another benchmark, Transformer outperforms TTT by a super large margin? So if you look at this benchmark closely, there are 2 labels where one is called TF fine-tune and the other is TF pre-train. The difference between the two has to do with how transformers are typically trained for longer context. For TF pre-train, the transformer model is trained on the fixed context from scratch, while TF fine-tune is only pre-trained on AK context, then fine-tuned further depending on how long the context you want it to be. The latter is the current standard practice of training a long context LLM and also shows how it scales better than TF pre-trained. However, due to the fine-tuning, the model had the chance to train for an extra 20%, which causes the increase in performance. And this does certainly provides an advantage to the baseline, but no matter how well Transformer can perform, it still cannot escape the quadratic complexity, and that is the reality. So the authors argued that the benchmark where the flops are matched makes more sense than just comparing models with the same parameter counts. And as Transformers still grow quadratically, TTT-based models might be bigger in size, but cheaper to train or even potentially outperform Transformers trained with the same cost. Additionally, if you look at its generation latency, while Transformers are growing linearly, TTT and Mamba methods are completely flat, with no increase in latency or whatsoever the longer the context window is. Throughput barely decreased too, I mean only for Mamba and TTT linear. TTT MLP does lie flat, but in a slow way unfortunately. So there are a lot of directions TTT can potentially go. With TTT MLP performing the best when flops are matched, it also suggests that Transformer backbone might be more suitable for larger models and longer context beyond their evaluations. But unfortunately, they were only able to test up to 32K context length due to the cost of training LLMs. And the authors predict that as now TTT layers are able to have more expressive hidden states, the Mamba backbone with temporal convolutions might become unnecessary, as TTT MLP might actually scale better. And as you can see, Mamba only excels in smaller toy examples. Additionally, they did also propose implementation speedups like wall clock time that contributed heavily in the reduction of inference and training time, but that may be too technical for this video. So yeah, this is definitely a promising and a fun paper. Shout out to the first author, Karen, for helping me out with this video. The main idea of TTT is not completely new, but this is still the first one that has actually done this much ablation studies while scaling that big. And a really cool future direction for this is to actually try out different types of inner models. Like for embodied agents or video generations, it could be replaced with a convolutional neural network instead of MLP or linear model. It could even be an entire transformer model, who knows? And if you want to keep up with the latest AI research, definitely check out my newsletter where I publish research breakdowns on many cool papers that I don't have time to make videos for. And thank you guys for watching. A big shout out to Andrew Lescelius, Chris LeDoux, Alex J, Deagan, Alex Maurice, Miguilim, FiFaŁ, Robert Zawiasa, and many others that support me through Patreon or YouTube. Follow my Twitter if you haven't, and I'll see y'all in the next one.